Approximately a third of this course will cover derivatives and their applications. But what is a derivative anyway, and how does it relate to things that we've already learned about functions? So the way we're going to start our discussion of derivatives is by talking about slopes. Okay? So when we have a straight line, we talked about slope mostly with straight lines. So we have a straight line, and a straight line has a slope, which we define to be the rise over run. And slope, wherever you calculate, as any right angle triangle you draw here, the rise, the value of the slope equals rise over run, is a constant. We have the same slope no matter how we take it. Okay? So a straight line has constant slope, dot, 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 but a curve does not. Okay. So when we're looking at a curve, the only way we can really take a slope, so we have a curve that goes something like that. The way that we can think about the slope at a curve is we could think about the slope of some line that is sort of close to the points. We would call this line that goes through 2 points a secant line. Or we can think about a tangent line. And a tangent line is a line that passes through exactly 1 point on a curve and no more in a specific region. Now the line could pass, it could become a secant as we continue, but a tangent is that line that goes there. So we can measure the slope of a tangent line or a secant line, but how do we calculate what the slope of a tangent line would be? Well, that is going to be where derivatives come in. So let's first look at what happens with a secant line. So our slope is delta y over delta x, where delta means change. So the change in y over change in x. Change in y over change in x, and change is positive or negative. Okay. The other way you may have seen it written is y2 minus y1 over x2 minus x1. We're taking the difference between the y's and the difference between the x's. Okay, so let's just recall how we find the slope of a line. So let's find the equation. I'm not just going to find the slope, we'll find the equation of a line through 1, 2, and 5, 3. Okay, so our slope, m, is delta y over delta x, which is 3 minus 2. We're subtracting the y's over 5 minus 1. We're subtracting the x's in the same order, which is 1/4. And we know that y equals 1/4 x plus b. We'll plug in an x and a y, probably pick the smaller one. So let's plug in x equals 1 and y equals 2. So 2 equals 1/4 plus b. So we take away 1/4 from 2, which leaves us with 7/4 is b. So we can write our equation here as y equals 1/4 x plus 7/4. We could also have used slope point form. Okay. So what happens if we want to find the equation of a line tangent to the curve, to a curve? Okay. So find the equation of the line tangent to the curve f of x equals x squared at 1, 1. Okay? So what are we going to do? Well, how do we even find what that tangent line is? So we know that it goes through exactly 1 point. What we're going to do is, rather than trying to draw a tangent line, we are going to draw a secant line and then take the limit as the secant line gets closer. The 2 points that the secant line passes through get closer and closer and closer together. So let's see right here, we have 1, 1, which is a point on our graph. And so what I'm going to do is I'm going to think of an x that's maybe a little ways away, where the distance here between 1 and this line is h. So this would be the point x equals 1 plus h. So we're going to take a point that's just a little ways on, okay? That would make this right here 1 plus h squared, because f of x is, f of 1 plus h would be 1 plus h squared, because f of x is x squared. So that's 1 plus h squared. So that's my y value. So what I'm going to do is I am going to set up the slope. So we're going to look at what m of the secant line is. Okay? So m of the secant line is going to be the second point, the y's, so 1 plus h squared minus the y at our original point, which is 1, over 1 plus h minus 1. So that's fine, but I don't want the secant line, I want the tangent line. So what we're going to think about, and I'm going to use a slightly different color here, let's go green. We want to think about this point getting closer and closer and closer and closer and closer to 1. So what we're talking about, we're thinking about getting closer and closer and closer till they're actually the same point, but we don't exactly know. We can't use this formula, however, if they are the same point. So rather than making them actually the same point, because then we lose that wonderful formula that we can just subtract the y values and subtract the x's, what we're going to do is we're going to take the limit as h goes to 0. So the limit as that distance between the 2 points gets smaller and smaller and smaller and smaller. So we're thinking of drawing closer and closer and closer and closer and closer and finding the slope of lines where the 2 points are closer and closer and closer together. And that is going to get closer and closer and closer to the slope of the tangent line. And as h goes to 0, that limit is going to actually be the slope of the tangent line. So m of the tangent line is the limit as h approaches 0 of 1 plus h squared minus 1 over 1 plus h minus 1. Okay? So we are now going to find this m. So this is still the limit as h approaches 0. We see that this is going to give us, if we plug in 0, we get 0 over 0, which means we've got a bit of math to do, as we know from our limits unit. So this is 1 plus 2h plus h squared minus 1 all over 1 plus h minus 1. This is equal to the limit as h approaches 0. We have 2 1s that cancel up here and 2 1s that cancel down here. And we can now factor out an h in the top. So we get h times h plus 2 all over h. And lo and behold, those h's cancel. And now I can take my limit as h goes to 0 because I no longer have an indeterminate situation. So this is equal to the limit as h approaches 0 of h plus 2, which equals 2. So what this is saying is the slope of the line tangent, okay? So the slope of the line tangent to the curve f of x equals x squared at 1, 1 is equal to 2. So now, if I want to find the equation of the tangent line, I just have to use the fact that it goes through the point 1, 1. So y equals mx plus b. I can plug in 1 for y and 1 for x, and I can plug in 2 for m. So 1 equals 2 times 1 plus b. And so b equals -1. And so the equation is y equals 2x minus 1. And if you go on Desmos and look at the graphs, you will see that that is in fact the equation of the tangent line. So although we did not name it such as we went through this example, this is finding the slope of the tangent line is finding the derivative of that function at the point. So we will go and give a definition of the derivative. Okay? And then we are going to look at finding some derivatives as a function. So ultimately what we're going to be doing, this is finding the derivative at a specific point. What we are going to want to do is find the derivative at any point. And when we find the derivative at any point, what we get instead of a slope or a number is we are going to get a function that for each value of x will give us the slope of the tangent line to the curve we started with at that point. So we are finding the slope. It's a function that gives the slope of the tangent line. So let's look at the definition of a derivative. The derivative of f at x, okay, which we will call, okay, f prime of x. I will write red, this reads f prime of x, okay, is defined as f prime of x equals the limit as, sorry, not x, as h approaches 0 of f of x plus h minus f of x, this is just the difference in the y's, over h. Why h? Well, the bottom could be, it would be over x plus h minus x, but x plus h minus x is always going to give us, so if we have f of x plus h, this is our y's from one point, minus f of x, this is our y and x from the other point. X plus h minus x is always just going to give us h, so we can leave that as is. It makes it a little bit simpler to remember. So that is the way that we define the derivative. Okay, we have a couple different ways we can write it. So in addition to f prime of x, we can write, okay, so f prime of x, that's our general, but we can also write it as y prime. We can also write it as d f of x with a big D. That's a less common notation. We can also write it as dy dx. And we can also write it as d f of x dx. All of these denote the same thing, which is the derivative of the function f at the point x. Okay, just a note that dy dx is not a ratio, so you can't just unpack it and treat it like a division problem. It doesn't work that way. It is a notation. Okay, historically there was the f prime of x is used in some cases. Leibniz, who sort of simultaneously to Newton came up with calculus independently, defined the derivative as dy dx equals the limit as delta x approaches 0 of delta y over delta x. But it was still the same idea that you're taking the slope of secant lines, that you're getting closer and closer and closer to being a tangent line, and that you are taking a limit to do this. Okay? Sometimes we may wish to evaluate the derivative at a specific point. So the derivative at point A is dy dx with the line here, which means evaluated at A. And we will also be using that notation for integrals later in this course. Okay, the process, just another word that you are going to see, of calculating the derivative is called differentiation. Okay, so what does the derivative look like when we think about it as a function? So let's take the graph of a function. Let's look at this graphically for a bit. Okay. So we have, and this is probably going to be a bit easier for those of you guys who have taken Physics 11, because you've seen, you're familiar with the process of trying to estimate the tangent line to a curve at a point. So if we have a lovely function here that goes like this, and then maybe goes down here, and then back up. Okay? The derivatives are going to be the slopes of the tangent line at certain points. So if I wanted to draw the graph, remember we said the derivative of a function is another function. We're going to get a function that gives the value of the slope of the tangent line at every point. So if we have right here, we have a flat tangent line, and we can see wherever this function turns around, we're going to have a flat tangent line. This is going to give us these zeros. If we take these right down here, this is going to give us the zeros of our derivative function. Okay, so what do we know how do we know what this function is doing? Well, we may not be able to get exact numbers, but we can estimate where a tangent line might go here. And we can see that at this point here that's drawn in blue that we have a negative slope, and it's a fairly steep negative slope. So this is going to go down at this point. The derivative will be down below the x-axis because the slope is negative. Here, we're going up, and the derivative is going up, but not quite as much. So this is going to be a point that's here up above the x-axis, but maybe not quite as high as this one is low. One thing to be really aware of is that just because the function is negative, it doesn't mean the derivative is negative. So if we look here, we've got a function. This has a positive tangent line. The slope of the tangent line is positive, but the function itself is negative there. The derivative at this point is going to be positive. And we don't know exactly what. We'll say it's somewhere around there. It's a little bit steeper than our positive blue line, so it might be a little bit above there. So if I now sketch in all of these points to draw the graph of the derivative function, we have another negative slope. So this is going to be down below. We're going to come up, and we can assume it's a relatively smooth curve. We turn around. We don't know if this is the high point necessarily. We come down again. We don't necessarily know if this is the low point. We come back up, cross through here, and come up here. We don't know if it turns back around or not at this stage. But notice that it's not tied to whether the original function is positive or negative. It's tied to what the slope of the original function is, or the slope of the tangent line, as that's how we define slope for a curve. Okay, so now you're going to see why we did so much stuff with calculating and evaluating complicated limits. So let's look at another example. if f of x equals root 2x minus 4, so radical 2x minus 4, find f prime of x. And we are going to find for the first time now f prime of x as a function and state the domain of f prime of x. Okay, so one thing we notice is that the domain of f of x is 2x. We have 2x minus 4 has to be greater than or equal to 0. So x has to be greater than or equal to 2. Okay? So we're going to use the definition of derivative to do this because we don't really have any other ways to do it at this stage. So f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. So we're going to plug in our specific function now. So we have the limit as h approaches 0 of radical 2 times x plus h. We're replacing all of our x's with x plus h in the first bit. So 2 times x plus h minus 4, radical 2 times x plus h minus 4, minus radical 2x minus 4, all over h. Okay, so when I plug in as h approaches 0, what do we get? We get radical 2x minus 4 minus radical 2x minus 4 over 0. So that's 0 over 0, which means we're going to have to do something. We have two radicals, you say. What should we do with two radicals that are being subtracted? Multiply by the conjugate, you say? What a fabulous idea. And here you can see where some of the preparation we did in limits is coming back to help us. So we have radical, we're going to multiply by radical 2 times x plus h minus 4 minus, plus radical 2x minus 4 all over radical 2x plus h minus 4 plus radical 2x minus 4, multiplying numerator and denominator by the same thing because we just must. So this is equal to the limit as h approaches 0. Now we have to sort out our numerator. Denominator, don't factor. Ultimately what we're trying to get rid of is that h by itself, so we are just going to leave it factored out. So we get 2x plus h minus 4 minus, in brackets, 2x minus 4 all over h times the beautiful 2 bracket x plus h minus 4 plus radical 2x minus 4. Okay, now we're going to simplify a bit. So let's see what happens. We have 2x plus h minus 4. So we have 2x plus 2h minus 4. So the 2x minus 4 minus 2x minus 4 is going to go away. So all we're going to be left with in the numerator is 2h. So this is the limit as h approaches 0 of 2h over all this beautiful, beautiful stuff. So radical 2 bracket x plus h, make that radical longer because we've got so much beautiful stuff down there, radical 2x minus 4. Okay, so now we can see the h's will cancel. Oh, need my closed brackets as well. Okay, so now we're left with a 2 in the numerator. So we have the limit as h approaches 0 of something with a 2 in the numerator, which is beautiful because the nice thing about this is we can actually evaluate this limit now. Okay, so it's 2 over all of our stuff. So let's not even bother taking the limit. We can just plug in our h. It's going to be either undefined or it's going to actually happen. So we plug in a 0 for h. We get radical 2x minus 4 plus 2x minus 4. So we have 2 over 2 radical 2x minus 4. because this is, once we plug in the h, this and that are just going to be the same, so we double it. Then we can cancel here, which leaves us with 1 over radical 2x minus 4. So as we notice here, this actually has nearly the same domain, except that 2x minus 4 has to be greater than or equal to 0, but it also cannot be equal to 0 because it's now in the denominator of our fraction. So 2x minus 4 is greater than 0, which means x has to be strictly greater than 2, giving us x is in the open interval between 2 and infinity. So that actually makes sense because at the end point, if you think about what a radical looks like, you can't draw a line tangent here. And we're going to talk briefly about differentiability and how a function is, when can we take the derivative. And you can see along this radical, we can take the derivative at any point except that very first point. Okay? So, differentiability is what we call the ability to take, the derivative at a certain point. So here's our definition. A function is differentiable at a if f prime of a exists or is defined. It is differentiable on an open interval AB if it is differentiable at every point on the interval. Okay. So where are functions not differentiable? Okay, so functions are not differentiable at any type of discontinuity. So it doesn't matter whether it is we're going to call our points A for all of this. It doesn't matter whether it is a jumping discontinuity or an essential discontinuity where we have some kind of asymptote, or even if it is just a removable discontinuity. Even if you have a removable discontinuity like that, it is not differentiable at this point. Okay, so how else? We may have a vertical tangent. Okay, that is another, if we have a vertical tangent line, which does occasionally happen with a function, and one example of that might be the cube root of x will have a vertical tangent just for a moment. Okay, so that is a vertical tangent and it is not differentiable at that point. We also may see some kind of corner. So that is where we can have something lovely like this. Okay. So number 3 is a corner, and of course our favorite, the absolute value function. Any absolute value function with a sharp corner like that, it is not differentiable at our point. We'll say A, and we'll say A. Okay? It is not differentiable at that point. So, we have a theorem about differentiability and continuity. You may see that some of these are the first one is about discontinuity, but the second two are not. So we have a theorem which says if a function is differentiable at A, then it is continuous at A. Notice that this does not work the other way, because we have some continuous functions like absolute values that are not differentiable. Okay, so if it's differentiable at A, then it's continuous. So let's look at one last example and see if we can tell where is the function f of x equal absolute value of x minus 1 differentiable. And we're going to have to go back to our definition of the derivative. So first let's write this in piecewise form. So we have f of x is equal to x minus 1 when x is greater than or equal to 1, and 1 minus x, or the negative of that, when x is less than 1. Okay, so let's look at our two cases. X greater than 1. Okay, so case 1, when x is greater than 1, f prime of x, okay, is equal to the derivative, the slope, of x minus 1 dx. Well, x is a line, it has a slope of 1. That is our derivative. So the derivative of a line is always just going to be the slope of the line. Case 2, because the tangent line, there is no tangent, the tangent line is the same at every point, and it is the line itself. So when x is less than 1, f prime of x is the derivative of 1 minus x dx, and the slope of this line is negative 1. So again, slope of a line, derivative of a line is the slope of that line, because the slope is a constant. So now we have to think about, what about at x equals 1? Clearly it's differentiable. The derivative exists both places, so it must be differentiable, because anything is differentiable whenever the derivative exists. We don't know if the derivative exists at x equals 1. So let's think about some partial limits. So let's think about the limit as h approaches 0 from below. So this is going to use the right-hand function of 1 minus x. So this will be 1 minus x plus h minus x minus 1 minus x over h, which equals the limit as h approaches 0 from below. Again, we're using our negative function, so 1 minus x plus h gives us a minus h over h, which equals minus 1. So minus h over h, which gives us minus 1. And the limit as h approaches 0 from above is going to be x plus h minus 1 minus x minus 1 all over h, which is just equal to the limit as h approaches 0 from above of h over h, which equals positive 1, because we can cancel there, cancel there. Okay, we notice that these are not the same. So, because the limit from below does not equal the limit of above, limit as h approaches 0 of f of x plus h minus f of x all over h does not exist, because the two limit from the right and the limit from the left do not exist. Therefore, the function is not differentiable at that corner point, the point where it switches at x equals 1. Okay. Now, you may be looking at this thinking, it's a bit of a long lesson because we go through a lot of very basic ideas about derivatives. You may be thinking, wow, that's a lot of computation to find a derivative, and we're using limits a lot. We use the limit to define the derivative, but there are actually some really lovely shortcuts when it comes to computing derivatives and actually figuring out how to find the derivatives of specific function. So next lesson we will look at some of those shortcuts which make actually calculating derivatives quite a bit easier than you might think.